Hi, I'm Michael Hansen, and I think that today I'll present to you what will probably be my last video about, or my final video about the theory of gravitational lensing. Beforehand I have introduced the lensing equation, magnification, convergence and shear, and then critical lines and caustics, and I think now is the time to introduce some simple lensing models to show you what we can actually do with lensing and lensing models. Now, I might have mentioned before, but nevertheless I'll do this again now, that for most of our lensing systems we cannot find analytical solutions. That means that we cannot sit down with a piece of paper and then write all the equations down and then arrive to some solution. In order to find the solution for some of the most complicated systems, which actually is most galaxies and clusters of galaxies, we need to do numerical analysis. That is, we have to find an expression for these equations, approximation, and then calculate them using computers. For this video here, I will introduce, as you can see up here, simple models. In this particular case, I will assume a spherical mass distribution, and from that we can derive the Einstein Radius, and we can also look a little closer at a given model where we have a singular isothermal sphere. I will explain what this means in more detail. Alright, so let's begin. Let's first look at the Einstein Radius. So, as I've shown you the lensing equation before, let's write it up. I will not write it fully, I'll just make it in shorthand notation. We have the position of the source is equal to theta minus the scale deflection angle alpha. In the correct description, I have also b with respect to theta is equal to theta minus alpha, the scale deflection angle with respect to theta. These are all vectorial. Alright, we also know the deflection angle from general relativity, 4 gm over c squared, let's just say r. In actual notation it is, let's put psi in here. Like that, sorry. Psi, no. Psi, and then the mass enclosed inside. And then we can use the relation psi is equal to theta dl to shuffle it a bit around, and I'll do that later on when I introduce the more fully explained lensing equation. I'll just leave it up here. Psi is equal to theta dl. Alright. So we can also rewrite the lensing equation. We also know that alpha is equal, alpha dls, I think it is equal to alpha hat equal to ds. Let's just quickly pull it up here. Let's see, so this is the source, image, and we have lens here, so we have, this is dl, this is dls, and this is ds. Yes. Oh, sorry. Alpha ds. Alright, so we can shuffle this a bit around, so we get that alpha is equal to alpha hat ds over dls, is that correct? No, something is wrong. I can see now what's wrong. Yeah. It is ds and dls. There you go. And then we get this is equal to dls over ds. Sometimes you just have to use your intuition to see that something's wrong. Now we can rewrite the lensing equation to get beta is equal to theta minus alpha hat dls over ds. Now then we use we make an assumption that this is a spherical mass assumption that we have, and then we introduce the deflection angle using this relation here, and then we can finally get that beta is equal to theta minus 4gm c squared theta dls over dl ds. This is a very important equation, so I'll put it in a box. I'm going to erase it a little bit, but try to remember this exact equation here. Right? First and foremost, remember that we have a theta here and a theta here, but I'll write it up. Alright, so this is sort of a general derivation of this lensing equation where we assume a spherical mass distribution, and then we can add all the pieces together to get this equation here. And now I'll show you how we can actually arrive at the Einstein radius, which sort of defines, in most basics, it defines the position where we will see the Einstein ring, if we have one. So let me show you how to do that. So again, write up the equation I just shown you, beta. Now let's say in this case we assume, which we can do, that the lensing equation is in one dimension. So we have a one-dimensional system. This means that all our vectors become scalars, and so it becomes beta is equal to theta minus 4. That was a horrible G. 4gm over c squared theta dls over dl ds. Alright, so now we take a very particular example where the position of the source beta is in the exact center of the lens, that is along the line of sight. It is exactly in the center of the lens with respect to the line of sight. That means that we can set beta equal to 0, so we have 0 is equal to theta minus 4gm c squared theta dls over dl ds. Now the first thing I do is that I subtract theta from this equation. I do it on both sides of the equation sign, so I get theta, remember, sorry, not subtract, I add theta here. Theta plus theta is equal to 0, or 1, or 0, and theta plus 0 is equal to theta. So I get 4gm c squared theta dls over dl ds. And now you might already see where I'm going with this, because now I can, let's put these in here. Now I can multiply by theta. And that gives me, if I multiply theta over here, I get theta times something and then divide by theta, that is 1. over here I get theta times theta, that's theta squared. So I get theta squared is equal to 4gm c squared dls over dl ds. Now I hope you can all see what we can do. We can say that we say that theta squared is the Einstein radius squared. So in order to find the Einstein radius, I just define this as the Einstein radius squared. I find that the Einstein radius is equal to the square root of 4gm over c squared dls over dl ds. Just to recap so you can follow. First we had the one-dimensional lensing equation. We have simply reduced the two-dimensional lensing equation to one dimension. Then we say, what if we assume that we have the source at the exact center of the line of sight? That means if we have an observer here, then we have the lens here, and then we have the source out here. And all of these, the observer, the center of the lens, and the source lie on the same line, the line of sight. That is what we do here. Then we shuffle it a bit around. First we add theta. It means that we say theta theta minus theta is equal to 0. And then we do the same on the other side of the equation sign. So we get theta is equal to 4gm c squared theta dls over dl ds. And then we multiply, let's just put it in. So we add theta on both sides. And then over here we multiply by theta. So at first we subtract, we add theta, then we get theta over here, then we multiply theta over here, so we have something times theta divided by theta, that's 1. Over here we have theta times theta, that's theta squared. So we get theta squared is equal to 4gm c squared over dls times dls over dl ds. And then I just make a definition. I say that this is equal to the Einstein radius, so that in actual I can get the Einstein radius by taking the square root of this here, and then I can define it as such. So this is the Einstein radius. For this, you can take a given spherical mass assumption, a given spherical mass distribution, mass, size, some distances that you calculate from the redshifts, and then you can find where the Einstein radius is. This is important later on when we introduce the symbol, the singular isothermal sphere. But already here you can get an idea of how we can find very simple solutions to these problems. So let's continue. So the first thing we do when we want to introduce a singular isothermal sphere, or just SIS, we assume that the stars behave like an ideal gas. So we can say that P is equal to rho kt over n. Now by shuffling this a bit around and assuming isothermality, we can get that m sigma v squared is equal to kt. Then from that we can derive sort of two equations. We can derive that rho dot over rho is equal to GMR over R squared. And we can also derive that M dot R is equal to 4 pi R squared rho. So these are two differential equations, and then one particular solution for those are rho within R, the density, is equal to the velocity dispersion squared. This sigma here is the velocity dispersion of the galaxy, that is the velocity dispersion of the stars in the galaxy. Yes, squared. Sorry, it shouldn't look like a G. So, V squared divided by 2 pi G, 1 over R squared. And from that we can find the surface mass density sigma, like this, within this obnoxious variable psi, and it becomes sigma V squared over 2G times 1 over psi. Now this is sort of the basic equation for the singular isothermal sphere. The surface mass density is defined as such: the velocity dispersion of a galaxy over 2 pi, and then some distance ratio. Now, in this over here, where we have taken the ideal gas, this is where the isothermal comes from. Isothermal simply means that the temperature, if you will, is isothermal. It is the same all the way through the galaxy. All right. Now, let's define. I'll erase this, and from that equation you just saw, the surface mass density and the density, we can define the deflection angle. So we get alpha. Now, alpha is equal to 4 pi sigma V squared over C squared times DLS over ds. And for the single isothermal sphere, this is equal to the Einstein radius. Now, if we take another approach to define this deflection angle here, sorry, it shouldn't be, call it alpha. We take another approach in doing this, we can actually see in more particular why this is actually equal to the Einstein radius. But in this case here, you just have to trust me. It is so. But it's particularly this part here, you can redefine as, let's see, 4gm over c squared dl, right? Then you can hopefully agree with me that. And that is because the velocity dispersion here and the pi can also be defined as gm, as the mass. And then you can see it all falls out, and then we also have some distance variable, of course. Alright? But since that we can just easily define the deflection angle as, let's just call it hat, because it's what we have, right? But, no. I will call it a vectorial for this moment here, but in the next bit I'm going to redefine it in one dimension again. We can do that without losing any generality. in our system. So we can actually, as you again remember, we have that the lensing equation is equal to beta equals theta minus alpha. Then if we put that in here, we get, again, remember, one dimension, beta is equal to theta minus theta e. And then we have some distance relation, theta over the absolute value of theta. Now, hi. You have now witnessed the exact reason why I have tried to change from going from my DSLR camera to my phone camera. The problem is that my DSLR, when recording videos, can only record 30 minutes at a time, and it doesn't give any announcement or expression when that time is up. So what I actually heard was the shutter or the mirror flipping up long after the video has actually stopped. So I'll try to continue from where I were at the video you just saw, and then reintegrate it with the upcoming video. It's not so many minutes, so it hopefully won't take so long. Alright, so last part of your video you saw me write that we had a position of beta. We have the equation for the lens equation for the SIS, the single isothermal sphere, as beta equal to theta minus the Einstein radius times some angular distance relation, isothetas, both of them. And so when you solve this equation, you can do that. You get that theta plus minus is equal to beta plus minus theta e. Let's put a box around this. And why is this important? As I probably have mentioned, so I won't say so much about it, is that most of the equations, most of the calculations we're dealing with in gravitational lensing cannot be solved what we call analytically. This is an analytic solution, right? We can sort of solve. We can get the number of images and the position of the images on the back of a piece of paper. Most of the times when we calculate these things, we need to do numerical simulations or calculations. All right. So I think the idea was that I chose some numbers. Chose the position of the source equal to 2 and the Einstein radius equal to 4, I think it was. And then, as you can see here, we get two solutions. From this, we get a theta plus and a theta minus. So let's look at theta plus. It's beta, so it's 2, and it's a plus 4, that's 6, and for the minus, we get 2 minus 4, and that's equal to minus 2. So if we could sort of plot this on a single one-dimensional plot, we do it like this, where we have see 0. No, that won't work. Let's put some lines in here, 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 here. And let's say that this is 0, 2, 4, 6, minus 2, minus 4, minus 6. Alright, so as you can see, we have an Einstein radius of 4. Let's put that in blue. So this is the center, right? So we have the Einstein radius here, and we have it here, because it's on both sides. This is where the lens is. Let's put that in as green, and then put an L on top. Let's put the source in. It's at beta is at 2, so it's here. And put an S. And then let's put the two images in as black dots. So we have an image at 6 out here. Let's call it I1. And we have an image at -2. Let's call it I2. Alright, in the next video I'm going to show you this in a different way, a different representation. But already here you can see two very important things. First of all, you can see that except in the occasion where the source is at position 0, that is at the center of the lens with respect to the line of sight, one image will always be outside the Einstein radius and one image will be inside. Also, when the source go outside this Einstein radius, which also defines the caustics, we will only have this image out here that will get closer to the source. But anyway, as long as we're inside the Einstein radius, and this is, of course, in this case doesn't give much room to move at, we only have another option, and that is to put the source out here. But this is just a generalized example. We could make it more refined. But as long as the source is within the Einstein radius and not at the center, not at 0, the distance between the images and the source will always remain the same, as you can see here. And that comes from this linear combination, or linear combination, as you can see here. Alright, but this is the basic thing here is that by making an assumption about the mass distribution that we have, and assuming or using a one-dimensional version of the lensing code or the lensing equation, which we can do, we can arrive at an analytical solution where we can find the position of the images. Now, by doing some further calculations, we could also find the magnification of the images. But generally it is that this image out here will be more magnified than this image in here. Alright? I will now continue on the next video. Then we should probably have the one image around here less magnified, and the other image around here a little more magnified. Now, as you can see, for these two solutions we have one image outside the Einstein radius, let's just call it that, and another image inside the Einstein radius. So let's say, what if we said beta equal to 0? What would we get then? Well, I can hope you can already see it. Zero. So the first solution, theta plus, is equal to theta 0 plus 4. And the other is theta minus is equal to 0 minus 4. So this will give 4, this will give minus 4. Let's put that in. So we get, I put a little dot in here, one dot here, one dot here. But in actual what we see is an Einstein ring. A highly magnified image of the source all the way around. Now here you can also see why this is called a singular isothermal sphere. And we can see that by plotting a solution plot. You can do that like this. So we have one possible solution here and one possible solution here. And then if we put in a source somewhere, this dotted line here is, let's put it in here. Yeah, let's just do that. You can see we get one image here. Right? We can make a different solution plot. Let's see if I can make one where we actually get two images. There's a different way of representing these systems. A singular isothermal sphere, it's still a singular isothermal sphere. Get something like this, something like this. So as you can see, if I put a source here, we get one image here, and we get one image here. So this will be the image that is demagnified, and this is the image that is magnified. You can see now why it's called a singular isothermal sphere, because even when we have two images, we don't have a third image. I hope I have introduced to you in my previous videos the odd number theorem, that when we cross a caustic, the Einstein Radius is in essence the caustic, the inner caustic, we should get three images, not two. And this is because this is a singular isothermal sphere. If we added something like this, for example, then we would get a third image here. But then it's no longer singular. So the reason why it's called singular is because that this is not a continuous function, it is abrupt. And that is also why we don't get the third image. Alright? I hope now that you have become a little less, you have a little best picture of how we can explore gravitational lensing using simple lensing models. Now, the singular isothermal sphere, should I put that up? SIS, is actually used as a simple model for galaxies, because galaxies can actually be assumed to be singular and isothermal. But in general, we would use a more complicated profile like the d-pi profile. But the singular isothermal sphere can be used with, I think it's 2 or 3 parameters. The d-pi profile uses usually 6 parameters. And as I will show you, tell you about in the next video, the final video where I introduce, first of all, I have submitted and defended my master thesis. So the next video I'll show you will be sort of an exempt or redo of my master thesis defense presentation, where I will introduce what we call free parameters. Essentially, the parameters you use to model the SIS, the d-pi profile. In the SIS, it's the velocity dispersion and the radius. The two or three parameters that you have, you can also include a, because in lens tool it is an SIE, it's an ellipse. You can also include 2 more parameters, an angle position and ellipticity. In the d-pi profile you have many more parameters, but when you have galaxy-galaxy lensing, you usually have a number of multiple images, like 2 or 3 multiple images. So 2 multiple images would give roughly 2 constraints, I think it is 2 or 3 constraints, maybe 4. But you would need to have 6 free parameters for your d-pi profile, and hence since you have more free parameters than you have constraints, this will not work. So you cannot do it like this. You need to have at least as many constraints as you have free parameters. The SIS, it's much more simple because you only have 2 free parameters. So the final thing that I want to discuss with you before we begin to look at results is how a lensing code actually basically works. So what it is that we want to achieve using a lensing code. Well, if we go back to where we introduced the lensing equation, you can probably remember that the lensing equation is nonlinear, which means that we can always calculate the position of the source if we have the position of one or more images, and we can figure out the deflection angle. But we cannot invert the equation, so to say that we can find the images if we know the position of the source and we have some deflection. This doesn't work. So what can we do with a computer where we try to analyze this? Of course, this goes for an analytic solution. We cannot analytically find the position of the images, or indeed how many images there is, even if we have a very good representation of the mass and we know where the source is. Cannot do that. Only explicitly for the basic model that I showed you before, like the point mass lens, or as I showed you, the singular isothermal sphere. That we can do because it has an analytical solution when we assume some mass distribution. All right, but basically, what is it that we're trying to do with the lensing code? So, what we have in the lensing code is the position of multiple images. I'm trying to draw this in 3D, so this will be in the image plane or lens plane. So what we can do in our model is that this is what we see. We see the images, and then we have some mass defined by some parameter, P1, P2, P3, so on, so on, so on. Parameters. So we have the images. I'll just call them 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. So we have images from 2 sources. We can find the distance to this mass, to the lens, using the redshift, and we can find the distance to these images, which is actually the source of these images, also by the redshift. So one way to optimize is to use the source plane optimization. This is easy and doable just right away because we don't need to invert the lens equation. Like I said, we can just calculate where beta is if we put in some deflection. The deflection angle, the scale deflection angle, is determined by the mass that we put inside here in the lens, and then we have the position of the images, and we can do that. So what we do in the source plane optimization, here we have the image plane, here we have the source plane, is that we project all these positions of the images down to a barycenter of the source. So for each image, we sort of get a barycenter of the source, and then if we look at that over here, so we can say that this is inside here we have the barycenter of the source. It is this dot here, and then we can find the position of one image here, the position of one image here, and one image here, and so on. And then, just erase the circle here and do it again. Use another color for the, this is the source, determined source position of the images. And then the error, the chi-square, is the different distance of the estimated source positions to each estimated difference between the barycenter of all the images, source position of all the images, and the distance to the individual images' source positions themselves. Now remember, all of which goes down here in the source position is estimated source positions from the math that we put in and the images that we have. But there's a problem, because the error we have is on the position of the images, and the error on the position of the images does not translate down to the source plane. So in reality, we are trying to compare something, do an error estimate on something that doesn't have anything to do with where we have the errors. So the best we can do in the source plane is that we can try to take, you can also call the mean value of this, it is the mean of the estimated source positions of all the images together, and then we try to find what is, this could for example be the source position for image 1,1. Then we try to figure out what is the distance from the source position, estimated source position of image 1,1 compared with the barycenter of all the sources, estimated source positions. And of course, the idea is that the better mass, the better the mass we put in here, the better parameter values we put in, the closer these values will be to each other, hence the chi-square will be smaller. But the true way to do this is in image plane optimization. Okay, so what does that entail? Well, I'm just gonna do it again. Let's look at image plane optimization. So let's just be clear. The idea with the source position, source plane optimization is that it's quick, it's fast. We don't need to invert the lens equation, so we can just do it. But the problem is that we have no real translation between the errors that we have on the image position and the source position that we estimate. So in essence, the source plane optimization gives a purely wrong result. So what is the true way to do it? Well, it's called the image plane optimization. And it has certain resemblances. I'm just going to do it with two images this time. We have the source plane here, sorry, the image plane here, and the source plane here. Image plane, source plane. So again, we put some mass in here, and then we have the images here. I'll just use two this time. So we do actually do the same again. We take this mass, and then we try to calculate the best position of the source. But what we do then is, given this mass that we have here, the parameters that we have, this source position here, we try to backtrace to see, let's give it another color, to see where does the images actually get. Now the problem is, as I will try to show you here, is that when we backtrace this, and that is the non-linearity of the lensing equation coming into play here. So as you can see, what we do is that we take this mass, the parameters that we have in our model, we take the images. Given this mass, we try to find out what is the deflection. Now, just remember that what you don't see here is us. We are out here. This is the telescope. and this is what we actually see. But as for now, this part here is not important. This is not important for the lensing code. It doesn't have to know where we are as observers. It only needs to know where the images is and what mass we want to try it with. So let's get back on track. So what we do is that we put some mass in here, then we take the position of the images that we have and try to figure out where is the position of the source. When we have this best position of the source, this is the barycenter, then we try to use that source position. Given this source position and this mass here, how would it produce images? Now, as I've tried to show you here, is that even if we have this mass here giving a perfect position of the source, we can end up having 4 images instead of 2 with widely different varying positions of the images, and we have to reject that model. So we could try it again and again and again, and at some point we might end up with a situation where we only get 2 images from this code here. From this source position here. There's still a difference in the position of the images compared. This is the predicted. The red is the predicted. Should we put that? Blue, actual. Red, predicted. So, and this is of course is the source position. Maybe I should make that green just to. So green is barycenter of source predicted. So it's still predicted. All right. So let's try to take it from the bottom up. Now we have a model where we put in some parameter values here. We use these parameter values to figure out where the most likely position of the source is. It's the green, the barycenter, given these 2 images. Then we use that most probable source to figure out where would the images be given this mass. And this time we get 2 images, but they differ. So what the lensing code does in the image plane optimization is that, should I write that? Image plane optimization is that it keeps refining these parameters here until the images here gets closer and closer to the actual images. Now, the reason why this method is better is because what we give the model is the position of the images, and of course the best thing to compare with in order to find the most likely set of parameter values is of course the image position. It is also here we have the actual error on the position of the images. The problem with the image plane optimization is that it is slow. It takes a lot of time because, like I showed you before, we can end up having models where we get more or less images that we actually have. The positions is highly deviating from the actual images that we give the model, and so on. But eventually we end up hopefully with a model where they converge, so the predicted images is closer to the actual image positions. Maybe I should do it like this, so you can better see that this is image position. So this is basically what a lensing code does. So let's put it up, what the differences is. It can be set so sort of very easily. Source plane, image plane. Of course, I'm talking about optimizations here. So source plane optimization, it's fast, but it's wrong. Image plane, slow, many rejected models, but it is ultimately correct. You can also say in parentheses this is imprecise, this is precise. So what we do when we run these codes is that we try to use this to sort of narrow parameter space. For example, if I say that the parameter space for a given halo should be, that the parameter space should be something like minus 50 to 50 arc seconds. So it would test the center, called X. Let's say the same with Y, 50. So it would test, and let's give it a precision of 0.01, something like that. So it would test all the parameter values within minus 50 to 50 with a 0.001 precision until it finds what's the best position. Now, I can use the source plane optimization to sort of refine this space here. So what I give the image plane optimization could possibly be something like, let's say we refine the model here. So here we could, for example, give it, it might be minus 15 to 20, minus 15 to minus 20, and Y could be 10 to 40. Something like that. Now you can see I still have some parameter space that I need to explore, but at least I have narrowed in the field, because even though the source plane optimization is essentially wrong, it's not completely random. It has something to do with the images that I give the model or the code. It's just not very precise. So now you have an understanding of how a lensing model basically works. Of course, there's a lot more to it, but this is basically how we do it. In essence, we give the lensing code some image positions, then we try to define the mass using some parameters, then we shift those parameters around until either in the source plane optimization we get the least difference between the barycenter of all the images for a given source. If I have two different sources, I have two different barycenters, but given that the barycenter of all the images from the same source and the predicted source position of the individual images, but also, and then do this in the image plane optimization, do the same thing, find the barycenter, and then try to find the predicted images using this barycenter here. So that's basically how a model works, and then I shift the parameters around until either the source plane optimization gets the lowest chi-square, the lowest difference, or the image plane optimization gets the lowest difference between the image position, predicted image positions, and the actual image positions. All right. The next value will undoubtedly be about my master thesis defense and a lot of general ideas about the analysis I did on the clustered max JO for 16.1/2403. Thank you for watching.